Welcome to the 6th video in our Unit 2. So this is the second to last one. And here's a fun little word for you. It is the penultimate video of our second unit. Let's start with recapping our two newest equations. Now, again, the rearranged one is not really that new. And then our second one is definitely new. We derived that from the graph. So we've got these two equations. To come up with the third equation, we're going to combine the two together. So we're going to sub equation 1 directly as it is into equation 2. When we do that, we will get, so this is where we're going to be subbing in, because we're subbing in 4v, because v equals v naught plus at. So we've got v naught plus at. And then back to the rest of the equation, plus v naught times t all outside the brackets. Okay, so now we've got to do a little bit of rearranging, combining like terms. 1/2, we've got 2v naught, so let's write 2v naught plus at. And multiply that by t on the outside. What I want to do now, I'm going to do it all in one step. I'm going to multiply and expand the brackets. So the 1/2 and t, I'm going to multiply to both of those terms inside the brackets. So 1/2 times 2, that cancels out, so we end up with v naught. I'm multiplying it by time as well, so v naught t. And then we're going to multiply 1/2 t times at plus 1/2 a. And then t times t becomes t squared. That is displacement. So we've got d equals v naught t plus 1/2 t squared. This is our third equation. This is going to be the most used equation we have this year, just because it's got the most useful things. And it also can be used in a lot of different situations. So there's two specific equations that we might have to work with that come from this one. So this is assuming our initial position is 0, which is almost always the case. But if it's not, we can add on to the equation just a little bit to account for the initial position not being 0. So here's the original. And if we just add a d naught, that will satisfy a non-zero initial position. That will rarely happen, but it's in your notes if you come to a problem that needs it. Now, what happens more often is that we have an initial velocity of 0. So if you remember grade 10, dropping something had an initial velocity of 0. That one we're going to come to a lot when we do gravity in the next video. So if the initial velocity of 0 of our original number 3 equation, that means v naught is 0. v naught 0 times time is just going to be 0. So we get left with 1/2 at squared. Again, it's the same equation. We've just simplified it for an initial condition that might come up quite often. So let's use this equation in the first problem, and then we can go through the second one in class. So a car starting from rest accelerates uniformly at 3.4 meters per second squared. So that's my acceleration. And it goes for 8 seconds. And we're looking for displacement. How far does it go? Well, it starts from rest. That means our v naught is 0. So we just came up with this equation that simplified to 1/2 at squared right here, because our initial velocity is 0 in this problem. Then we can just plug everything right in there. 3.4 meters per second squared times 8.0 seconds. And the time is squared. Make sure when you plug it into your calculator you get 8 squared, which is 64. So make sure that you're doing that in your calculator or else you're not going to get the right answers consistently when you're using this equation. So I plug this into my calculator, and I get, right out of my calculator, it tells me 108.8, and the units will be meters. Now I know I'm not done because that is what my calculator gave me. That's not what proper sig figs are. Let's move over here and let's think about sig figs. Everything's multiplication, multiplication rule. The least number of sig figs is what our answer should have. Both of our numbers have 2, so our final answer should have 2. So we're going to round it to 110 meters is our final answer. So do this next problem. It will involve the original equation. So this one here, v naught t plus 1/2 at squared. You might have to do a little bit of rearranging, but try it out, see how that one works. Now, I said there's 4 equations. Now, let's come up with the 4th one. Again, we're going to start with our original 2. V equals v naught plus at, and d equals 1/2 v plus v naught times t. Now we're just going to solve something a little bit differently. We're going to solve equation 1 for t. When we do that, we get t equals v minus v naught all over a. Now it seems very suspicious to want to do this, but you have to kind of sometimes know where you're going to know why you're doing it. Now we're going to put that into equation 2. The reason we're doing that is we want to get rid of time. All of our equations have time. So if we come up with an equation that does not have time as a variable, that can be very, very useful for us. So d equals 1/2 v plus v naught. Now we're substituting in for time with this new equation, so that's going to give us v minus v naught all over a. Now we have to use some of the math that you never thought you were going to have to use, but time to go do it. We're going to rearrange, and somehow we're going to end up for v squared. So if you can't see where that's coming from yet, just hold on and we'll get there. I know I want to get v's all by themselves, so I'm going to get rid of the 1/2 and the dividing by a first. To do that, I'm going to multiply by 2a, so I'll get 2a d, and that's going to be equal to v plus v naught times v minus v naught. Should make sure that I've got my vector arrows on here all the time. Okay, that is a very specific binomial. If you remember math, that is a difference of squares, which you can expand it out the very long way. But I know what the result's going to be because I've done this a lot of different times. And again, knowing a difference of squares also makes my life very simple. So I know the answer will be v squared minus v naught squared. Now that, I'm not going to be drawing the vector symbols on there because when you square things, they don't quite come out to be the same. So we're not going to necessarily have vector symbols on those two values. When they're squared, the negative signs disappear anyway, so it's not very useful. You just have to remember to do the plus or minus when you square root if you have to solve for v or v naught. And as I said, we're solving for v squared, so we have v squared equals v naught squared plus 2ad. Once the v naught squared gets moved over to the other side, it becomes positive. So we have v squared equals v naught squared plus 2ad. That is our fourth equation, and it is without time, which is very, very useful for us. So let's take a look, because sometimes time is very difficult to measure. Let's look at this example here. An automobile starts at rest, speeds up 3.5 meters per second squared. And when the light turns green, how far has it gone when it's traveling 25 meters per second? So, starts at rest, v naught equals 0 meters per second. Acceleration equals 3.5 meters per second. And v equals 25 meters per second. And we're looking for how far it has gone, so our displacement. So, let's go into our equation. V squared equals v naught squared plus 2ad. So I want to solve for displacement. That's what I want to do first. So I'm going to rearrange it a little bit. Before I plug in my numbers, it's a good habit to get into. You're less likely to miswrite a number, forget a direction, or many other simple things that can go wrong. Now, plugging in my numbers, 25 meters per second. And that's squared minus 0 meters per second squared. That's fairly easy to calculate. Over 2 times 3.5 meters per second squared. And our calculator will give us an answer of 89.2857 meters. If you wrote that as your answer, you're going to lose marks because we're not as accurate as that number says we are. We need to figure out our sig figs. With the -0 makes it a lot simpler, because everything we're doing then becomes multiplication or division, so we're just trying to match the least number of our sig figs. Both of them have 2, so our final answer should have 2, which comes to 89 meters, because 2 will round down, so we get 89 meters as our final answer. So both of those equations today are definitely the most used, because one doesn't have time and the other has displacement, time, acceleration, and initial velocity. So it's got a lot of different things. Between all of these equations, we can solve for any of the variables. Depending on your situation, you have to know which equation you can use. So you've got this fun chart here that as long as you know 4 variables, if you know 3 variables and you're looking for the 4th, one of these equations will be useful to you. You'll get more familiar with them as you use them more, but for now, you can take a look at this chart to help simplify your problem-solving technique as you're still getting lots of practice in. As always, physics is awesome.